In this video, we discuss the meaning of the concepts and formulas related to circular motion that we've been using in the previous videos in this series. If you're not interested in or don't have the time for this discussion, then you can skip to the next video, which contains another circular motion problem. To begin, let's discuss the axes for motion in vertical and horizontal circles. Let's consider motion in this vertical circle and motion in this horizontal circle. Please pause the video and try this problem. Now here's the answer. Notice that it's okay to choose different axes for different points along the path of motion. The z-axes should be understood as pointing perpendicular to the plane of the page. These z-axes point directly out of the page, and this z-axis points directly into the page. The z-axis usually doesn't play an important role in the solution for typical circular motion problems. So when you're solving circular motion problems, it's usually not necessary to draw the z-axis. In this video, however, for the benefit of our own understanding, I will draw the z-axes. At each point along the circle, we choose a radial axis that points towards, rather than away from, the center of the circle. At points B, D, E, and F, the radial axis is the x-axis. At points A and C, the radial axis is the y-axis. At each point along the circle, choose a tangential axis that is tangent to the circle at that point, and that points in the object's direction of motion. At points A and C, the x-axis is tangential. At points B and D, the y-axis is tangential. At points E and F, the z-axis is tangential. Next, let's discuss the velocity vector for circular motion. Please pause the video and try this problem. Now here's the answer. The direction of the velocity vector indicates the object's direction of motion. So, the velocity vector at any point along an object's path of motion will be tangent to the path at that point. So, for circular motion, the velocity vector at any point along the circular path of motion will be tangent to the circle. Using this rule, we can draw the velocity vector at points A, B, C, and D along our vertical circle. It would be awkward to draw the velocity vector at points E and F on the horizontal circle, but we can describe the velocity vector at point E as pointing tangent to the circle and directly out of the page. So the velocity vector at point E will point in the direction of the positive z-axis that we chose for point E. And we can describe the velocity vector at point F as pointing tangent to the circle and directly into the page. So the velocity vector at point F will point in the direction of the positive z-axis that we chose for point F. Next, let's discuss the acceleration vector for circular motion. The velocity vector indicates the object's direction of motion. The acceleration vector does not indicate the object's direction of motion. So what does the acceleration indicate? In physics, the term acceleration refers to speeding up, or slowing down, or changing the direction of motion. We can use these rules to help us interpret the acceleration. Now please pause the video and try this problem. Here's the answer. The radial component of the acceleration always points towards, rather than away from, the center of the circle. So we can draw the radial components of the acceleration as I've shown here and here. Now, what is the meaning of the radial component of the acceleration? The radial component of the acceleration is always perpendicular to the velocity. So, the radial component of the acceleration measures how quickly the object must change its direction of motion in order to maintain its circular path of motion. This is one of the key ideas for this video, so let's repeat it. The radial component of the acceleration measures how quickly the object must change its direction of motion in order to maintain its circular path of motion. If an object is motionless in a component, then that component of the object's acceleration will be 0. When an object moves in a circle, the object will be motionless in the component that's perpendicular to the plane of the circle. So, when an object moves in a circle, the component of the acceleration that's perpendicular to the plane of the circle will be 0. So, for an object moving in a vertical circle, a sub z will be 0. And for an object moving in a horizontal circle, a sub y will be 0. We've seen in the previous videos that the tangential component is usually not important for solving typical circular motion problems. But for the sake of our own understanding, we can interpret the tangential component of the acceleration like this. If the tangential component of the acceleration is parallel to the velocity, that means that the object is speeding up. If the tangential component of the acceleration is anti-parallel to the velocity, that means that the object is slowing down. And if the tangential component of the acceleration is 0, that means that the object is moving with constant speed. Motion in a circle with constant speed is referred to as uniform circular motion. Next, let's discuss the meaning of the concept of net radial force. According to Newton's first law, if the net force on an object is 0, then an object in motion will continue to move in a straight line at constant speed. Let me repeat that key idea. If the net force on an object is 0, then an object in motion will continue to move in a straight line at constant speed. So, in order to move in a circle rather than in a straight line, there must be some force which changes the object's direction of motion so that the object will move in a circle rather than in a straight line. The force that changes the object's direction of motion so that it will move in a circle rather than in a straight line is called the radial force. Of course, there could be more than one force in the radial component. According to Newton's second law, the net radial force will determine the radial acceleration. Again, to repeat that key idea, according to Newton's second law, the net radial force will determine the radial acceleration. These are key ideas for understanding circular motion, so I suggest that you pause the video and study these ideas for a bit. In the problem that we covered in video 1, the radial force was provided by T sub x, the x component of the tension force exerted by the string. In the problem that we covered in video 2, the radial force was provided by the normal force exerted by the wall of the cylinder. In video 3, the net radial force at the bottom of the circle is the vector sum of the normal force and the weight force. At the bottom of the circle, the normal force and the weight force point in opposite directions. So the net radial force is the result when the normal force is partially canceled by the weight force. At the top of the circle, the net radial force is again the vector sum of the normal force and the weight force. But at the top of the circle, the normal force and the weight force point in the same direction. So at the top of the circle, the net radial force is the result when the normal force is reinforced by the weight force. Next, let's discuss the meaning of this formula for the radial component of the acceleration. This formula determines how big the radial acceleration has to be in order for the object to maintain its circular path of motion. In other words, this formula determines how quickly the object has to change its direction of motion in order to maintain its circular path of motion. In this formula, speed is on the top of this fraction, and radius is on the bottom of the fraction. So this formula implies that increasing the object's speed while holding the radius constant will increase the radial acceleration. But if we increase the radius while holding the speed constant, that will increase the bottom of this fraction. Increasing the bottom of a fraction makes the fraction as a whole smaller. 4 is a bigger number than 2, but 1/4 is a smaller number than 1/2. So this formula implies that increasing the radius will decrease the radial acceleration. Do these implications of the formula make sense? When the object is moving with greater speed, while holding the radius constant, the object does indeed need to change its direction of motion more quickly in order to maintain its circular path of motion. So when the object is moving with greater speed, it does indeed make sense that the radial acceleration must be greater, just as this formula predicts. Think about driving around a curve. It's more dangerous to drive around a curve at high speed rather than low speed, because the higher the speed, the greater the required radial acceleration. The higher the required radial acceleration, the higher the required radial force. And the higher the required radial force, the more likely that the actual radial force will not be large enough to do the job, in which case the car will skid out of the turn. That's why it's more dangerous to drive around a curve at high speed. How about this result? Does this result make sense? A circle with a small radius corresponds to what we would call a sharp turn. A circle with a large radius corresponds to what we would call a gradual turn. Increasing the radius corresponds to making the turn more gradual. If we hold the speed constant, then in a more gradual turn, the object must change its direction of motion more slowly in order to maintain its circular path of motion. So when we increase the radius, holding the speed constant, it does indeed make sense that the radial acceleration must be smaller, just as this formula predicts. Think about driving around a curve. It's more dangerous to drive around a curve with a sharp turn rather than a gradual turn. Here's why. The sharper the turn, the smaller the radius of curvature. The smaller the radius of curvature, the greater the required radial acceleration. The greater the required radial acceleration, the greater the required radial force. And the greater the required radial force, the more likely that the actual radial force will not be large enough to do the job, in which case the car will skid out of the turn. So this formula corresponds to the common sense idea that it's more dangerous to drive at high speed around a sharp turn, and it's safer to drive at low speed around a gradual turn. Next, let's discuss how the amusement park ride from the problem in video 2 prevents the riders from slipping. How does this amusement park ride prevent the riders from slipping after the floor drops away? The normal force will adjust to be whatever size it takes in order to maintain the rider's circular path of motion. The static friction force will adjust to be whatever size it takes in order to prevent the rider from slipping downwards, up to the maximum limit imposed by this formula. The ride is operated at high speed. At high speed, a large radial acceleration is required in order to maintain the rider's circular path of motion. To provide this large radial acceleration, the normal force will adjust to provide a large radial force. But a large normal force means that the wall is pressing firmly against the rider, which implies a large maximum static friction force. A large maximum static friction implies that static friction will be able to adjust in order to be large enough to prevent the rider from slipping downward. So, by operating at high speed, the ride causes the wall to press firmly against the rider, which allows the static friction to be large enough to prevent the rider from slipping downwards. Next, let's discuss whether our results from the problem in video 3 make sense. Here are our results for the problem from video 3. Let's begin by asking whether our result for n makes sense. The magnitude of the weight force is mg, so our result says that the magnitude of the normal force equals the magnitude of the weight force, mg, plus something extra, mv sub b squared over capital R. Does that make sense? Well, the normal force has two jobs, so to speak, at the bottom of the circle. Job number 1, the upward normal force has to cancel out the downward weight force. And job number 2, the upward normal force has to create the upward radial acceleration, which is necessary for the pilot to maintain their circular path of motion. So yes, it does make sense that the magnitude of the normal force equals mg to cancel out the weight force plus mv squared over r to provide the upward radial acceleration which is necessary for the pilot to maintain their circular path of motion. What about our result for v sub t? Does this result make sense? Well, our result for v sub t mathematically implies that v sub t is greater than v sub b. Here is a proof that our result for v sub t mathematically implies that v sub t is greater than v sub b. Now, does it make sense that v sub t is greater than v sub b? Does it make sense that the pilot's speed at the top of the circle is greater than the speed at the bottom of the circle? The normal force at the bottom of the circle points towards the center of the circle, but the weight force at the bottom of the circle points away from the center of the circle. That means that at the bottom of the circle, the normal force will be partially canceled by the weight force. On the other hand, at the top of the circle, both the weight force and the normal force point towards the center of the circle. So at the top of the circle, the normal force will be reinforced by the weight force. And remember that the problem told us that the magnitude of the normal force will be the same at the top and the bottom of the circle. So, the net radial force at the top of the circle will be greater than the net radial force at the bottom of the circle. According to Newton's second law, a greater net radial force implies a greater radial acceleration. So, the radial acceleration at the top of the circle will be greater than the radial acceleration at the bottom of the circle. According to this formula, if the radius is held constant, a greater radial acceleration implies a greater speed. So, in this situation, the pilot's speed at the top of the circle must be greater than the pilot's speed at the bottom of the circle. And that matches what was mathematically implied by our result. So yes, this result does make sense. The larger net radial force at the top of the circle will cause the pilot to change their direction of movement more quickly at the top of the circle. And if the pilot is changing their direction of movement more quickly at the top of the circle, the pilot must move with greater speed at the top of the circle in order to maintain their circular path of motion. Again, that matches what was mathematically implied by our result. So again, this result does make sense. Next, let's discuss the effect of the object's mass on circular motion. Loosely speaking, the mass measures the quantity of matter contained in an object. Don't confuse the mass with the weight. The weight measures the downward pull on the object due to the Earth's gravity. In video 4 of my previous video series on basic Newton's second law problems, I discussed the meaning of the concept of mass. In that video, we learned that a more massive object is more difficult to accelerate. That is to say, it's more difficult to speed up a more massive object, it's more difficult to slow down a more massive object, and it's more difficult to change the direction of motion for a more massive object. This is the part that's especially interesting for circular motion problems. We can confirm this idea using Newton's second law. Here again is Newton's second law for the radial component. Let's solve this equation for the radial acceleration. Our result is that the radial acceleration equals the net radial force divided by the object's mass. The net radial force is on the top of this fraction. So this result implies that increasing the net radial force while holding the mass constant will increase the radial acceleration. The mass is on the bottom of this fraction. So increasing the object's mass will increase the bottom of the fraction. Increasing the bottom of a fraction makes the fraction as a whole smaller. So, increasing the object's mass while holding the net radial force constant will decrease the radial acceleration. This confirms our earlier statement that a more massive object is more difficult to accelerate. To be more specific, for an object moving in a circle, we've confirmed that the more massive the object is, the more difficult it is to change the object's direction of motion sufficiently to maintain its circular path of motion. A more massive object is more difficult to accelerate. But, of course, a more massive object will also experience a greater downward pull from the weight force. So, increasing the mass of an object will have two separate effects on the result of a circular motion problem. Effect number one, increasing the mass will tend to decrease the radial acceleration. That is to say, increasing the quantity of matter contained in the object will make it more difficult to change the object's direction of motion sufficiently to maintain its circular path of motion. And effect number two, increasing the mass will also increase the object's weight. That is to say, increasing the quantity of matter contained in the object will also increase the downward pull on the object from the Earth's gravity. Because of these two separate effects of the mass, mass is a difficult and subtle concept to analyze. The greatest barrier to understanding physics is mixing up the concepts. Here are some of the concepts we've discussed in this video. To understand circular motion, it's crucial not to mix up these concepts with each other. To avoid mixing up the concepts, don't use the word it. Don't say it is tangent to the circle, or it measures how fast the object is moving, or it points towards the center of the circle. Instead, say the velocity vector is tangent to the circle, or the speed measures how fast the object is moving, or the radial component of the acceleration points towards the center of the circle, or the tangential component of the acceleration indicates how the object's speed is changing, or the component of the acceleration that's perpendicular to the plane of the circle is 0, or the net radial force changes the object's direction of motion. Don't say it measures the quantity of matter, or it represents the downward pull on the object from the Earth's gravity. Instead, say the mass measures the quantity of matter, or the weight force represents the downward pull on the object due to the Earth's gravity. Don't use the word it. Instead, whenever you refer to a concept, label the concept with a specific name or symbol. This advice applies to all the concepts that you will encounter in your physics class, not just the concepts we discussed in this video. And this advice applies not just when you're talking about physics, but even when you're just thinking about the physics concepts inside your own head. The biggest mistake made by physics students is mixing up the concepts. To avoid mixing up the concepts, don't use the word it. To conclude this video, here are some problems for you to try. And here's one more problem for you to try. Did you find this video to be helpful? If so, you can support the videos by using the PayPal donate button on my website to make either a one-time donation or a monthly pledge. You can visit my website by clicking the link on the screen or by using the link in the video description box. Thank you.